Hey there, in this video we're going to look at some pretty cool techniques we can use to solve radical equations that look a little different from the ones that we've seen so far, because now this radical equation has a variable not just inside our radical, but there's also a variable on the outside. But certain aspects of this problem are going to be the same as what we've seen so far. So our first step is still going to be the same. We want to get the square root in this equation by itself on one side of the equal sign. So this negative x that is outside of the square root, but on the same side of the equal sign as that square root, we need to figure out how we can move that to the other side. And you know what, actually, let me do this in a different color so that it's clear that we're changing the equation we had started with. So just in the same way that we can add numbers to both sides of the equation to get things to cancel out, I can add the variable x to both sides of our equation. So now we have the square root of 42 minus x is equal to x. And when we have a radical that's by itself in an equation, we've seen before that to get rid of that radical, we can square both sides of our equal sign in order to cancel out that square root. And when we square a radical, that will cancel out because those are inverse operations. So now we're just left with 42 minus x is equal to x squared. Now from here, the rest of the problem is going to look a little bit different from what we've done before solving radical equations, but it's not completely new. We're actually just going to go back and use some of the techniques that we had used to solve polynomial equations earlier, because that's what we're dealing with now, is a polynomial equation that has more than one variable with different exponents on them. So the best way to solve a polynomial equation is to first put it in standard form. And what standard form means is we want all of the terms in our polynomial to be on the same side of the equal sign, so that the other side of the equal sign is just equal to 0. And if possible, it's going to be easiest to solve this equation if the coefficient on this x squared term is just equal to positive 1. So when we're figuring out in this equation up here which side of our equal sign we want to move things over to, if we move x squared over to the other side of this equation, then we would have to subtract x squared from both sides. But that would give us negative x squared, and that's going to make solving the quadratic a little bit more complicated. So it'll be easier to solve this if instead we move these two terms over to this side of the equal sign. And we can accomplish that if we subtract 42 from both sides of our equation. Positive 42 minus 42 cancels out, and now we have negative x equals x squared minus 42, and let's also move this negative x over to the other side of our equal sign. And we can do that by adding it to both sides. Now I did this in two separate steps just so that you could see clearly what we're doing, but feel free when you're working on your own to add all of these terms to the other side in just one step if that's a little bit faster for you. Now when we add x squared plus x, these are not like terms. They have different variables, so we can't combine them together. We're just going to have to write them separately as terms in this polynomial. So we have 0 on one side of our equal sign, and on the other side we've got x squared plus x minus 42. And would you look at that, we've met one of our old familiar friends, the quadratic trinomial. So we've learned a lot of different techniques we can use to solve equations like this. The fastest way is probably to try and use our ABC factoring. So the coefficients of this polynomial are a equals 1, b equals 1, and c equals negative 42. So to separate this polynomial into factors, the puzzle that we need to solve is find two numbers that will multiply together to equal c, negative 42, and add together to equal b, which is positive 1. So a couple of numbers that will do that for us are negative 6 and positive 7. To get a negative number by multiplying, we know that we need to multiply a positive times a negative, and if we want the answer we get when we're adding to be positive, then we want the positive factor to be bigger than the negative factor. So let's break this apart into its factors, and we have 0 equals x minus 6 times x plus 7. Now to get our final answers and figure out what x is equal to, we can set each of these factors equal to 0 and solve for x, because what this equation is really telling us is that something times something else is equal to 0. And the only way that that can be true is if these factors, one or both of these factors, would have to equal 0. The only way to get 0 by multiplying two things together is 0 times something. So there are two possible answers here that could work for us, which we get by solving these two factors. If we solve the factor x minus 6 equal to 0, then that gives us the solution x equals 6. If we solve the factor x plus 7 equals 0, then that would be true if x is equal to negative 7. So these are the solutions to the polynomial equation that we just factored up here. But we've got to be careful and remember that the original problem we were working on was not solving a polynomial equation, but it was solving this radical equation. And whenever we solve a radical equation, it's possible we could end up with an extraneous solution. So just like we did before when we solved radical equations, we need to check these answers and see if they work or if they are extraneous, meaning that they give us something that doesn't actually make sense when we plug it back into the original equation. And let's give ourselves a little more space on a new screen to do that. So I've rewritten the original radical equation that we were solving before we had turned it into a polynomial. And the two possible solutions that might work that we got from solving our polynomial equation are positive 6 or negative 7. So to check those solutions, we want to plug those back into our original equation for x and see if the equation is true or not. Let's check positive 6 first. So we'll keep the original radical equation as it was written, except replace anywhere that we see x with positive 6. So instead of 42 minus x, we have 42 minus 6. And instead of minus x outside of our radical, we have minus 6. And we want to check that this really does equal 0. So if we simplify the inside of this square root, 42 minus 6 gives us 36. So we have the square root of 36 minus 6 equal to 0. And the square root of 36 is equal to 6. And 6 minus 6 equals 0. So both sides of our equation say that they are equal to 0. So that is true. So 6 is a valid solution. And we will say that x does indeed equal 6. And it's possible that x could also equal negative 7, but we need to check to make sure. So if we check -7 by plugging it back into our original equation, we're going to replace anywhere we see x with -7. So instead of 42 minus x, we have 42 minus -7. And instead of minus x outside of our radical, we have minus -7. And we want to check that this is all equal to 0. Remember, when we're checking these extraneous solutions, we don't want to move anything around in the equation or do things to both sides, because that's what could possibly create an extraneous solution. What we want to do when we check is leave the equation as it was written originally and just simplify each side separately. So the inside of our radical here will become square root of 42 plus 7, because negative times -7 is +7. And same thing outside of our square root, that will become plus 7. So this equation says the square root of 49 plus 7 is equal to 0. The square root of 49 is 7. So this equation is telling us 7 plus 7 is equal to 0. Well, of course, we know that that's not true. 7 plus 7 is equal to 14, and 14 is not equal to 0. So because that answer gave us something that was false, we would say that 7 is an extraneous solution, and it didn't actually work in the radical equation. So that's a pretty cool method that we just used, because it combined together our knowledge of solving radical square root equations and solving polynomial equations using factoring. Now let's recap and just keep track of everything we did to get to our final answers. We started off with a radical equation that had some variables inside and outside of the radical. And we first got the radical by itself by moving that x over to the other side. And then we squared both sides of the equal sign so that we could get rid of that square root. Once we're dealing with a polynomial equation, we moved all of the terms to the same side of the equation so that we could deal with a polynomial in standard form. We used factoring to solve that polynomial, splitting it up into the factors x plus 7 times x minus 6, and that gave us the solutions x equals -7 and x equals +6. But since the original equation that we started with was a radical equation, we need to check for extraneous solutions, and it turned out that -7 was extraneous, whereas +6 worked. So our final answer here is just x equals +6. All right, you ready to try out another one? Now, if you want to challenge yourself, I encourage you to pause the video here and see if you can try to work through this on your own and then play the rest to check your answer. Or if you'd like to work through it together, let's get started on doing that right now. So first thing we want to do is get the square root part of this equation by itself. And we can do that if we add this variable x over to the other side of our equal sign. So now we have the square root of 7x minus 10 is equal to x. Now we can get rid of the square root by squaring both sides of our equation. And we have 7x minus 10 equals x squared. When we squared that square root, those two things canceled out and we just had the terms that were left underneath. Now we want to put this in standard form so that we can solve it as a polynomial. And standard form is when we have 0 on one side of our equal sign and all of the other terms on the same side. And if possible, when we put this in standard form, we want to have this leading coefficient on x squared equal to 1. So if we keep x squared on this side of our equal sign, we already have 1x squared there. Let's move these other terms over by adding the opposite to both sides. If I subtract 7x from both sides, we can get that to cancel out. And if I add 10 to both sides, we can get that negative 10 that we had originally to cancel out. X squared and negative 7x are not like terms. They have different exponents. So we're going to leave them separate when we write this as a polynomial. And this is a quadratic trinomial that we can solve using factoring. So our puzzle is to find the two numbers that will multiply together to equal c, positive 10, and add together to equal b, negative 7. To multiply two things and get a positive number, we could multiply a positive times a positive or a negative times a negative. But since the number we're trying to get through adding is a negative number, that means that we need to use two negative numbers. So their product will be positive, but their sum will be negative. And the two negative factors of 10 that we can use are negative 5 and negative 2. So now we can separate this polynomial into its factors. X minus 5 times x minus 2. And if we set those factors equal to 0 and solve, that will give us two possible solutions. X is equal to positive 5 or x is equal to positive 2. Well, those are the solutions to this polynomial equation, but we also want to make sure that those solutions work in our original radical equation that we had started with up here. So let's plug those answers back into that radical equation one at a time and check to see that they really work. Let's start with checking positive 5. If we keep everything the same in the equation except replace those x's with positive 5, since we have negative x in the original equation, when we plug in positive 5, negative x becomes negative 5. And now we want to keep everything on the side of the equation that it's already on and just simplify this one side to see if it really does equal 0. Inside of our square root, we have 7 times 5 is 35. And 35 minus 10 gives us 25. The square root of 25 is 5. So we get 5 minus 5 is equal to 0, which says 0 is equal to 0. And that does work. That is true. So we would say that x equals 5 is a valid solution. All right, using some technological wizardry, I've cleared up some more space for us, and let's finish this problem by checking the other possible solution, x equals positive 2. So we're going to plug 2 back into our original equation, replacing anywhere that we had the variable x, and simplify the side of our equation to see that it really does equal 0. Inside our square root, we've got 14 minus 10, which is 4. Square root of 4 is 2. And 2 minus 2 does equal 0. So we get 0 is equal to 0. And that means that this answer is also a valid, not extraneous solution.